Hello everyone and welcome to another episode of Temple Chemistry Demonstrated. My name is Zishan and today we're going to talk a little bit about titrations. So right in front of me we have all of the equipment that you're going to use in lab, and let me go over it with you. So first we have this burette, kind of like a long cylinder, like a graduated cylinder. This has one purpose, and that is to basically dispense a known quantity of liquid into your flask. So how do we use this thing? Well, we want to always record two observations from the burette. No matter what you're doing, you want to record two things. The first is your initial volume, and that has to take into account the volume that is in the tip of the pipette. So sometimes when you fill up the pipette, the bottom of this is going to be empty. To avoid this issue, I always have an empty flask. I call it my waste flask, my waste beaker, and I want to drain a little bit of sodium hydroxide until I get to a nice clear number. Now, you can really stop it wherever as long as you record this accurately. I like to stop at a clean whole number, and that makes doing math later a little bit easier. So actually, right now, the burette is reading 21 milliliters, and I'm going to write that down as my initial volume. That's the first step in doing a titration. If you somehow forget to record this, you're basically screwed and you have to redo the entire process. So now what's next for a titration? Well, you would think with sodium hydroxide, you could just take some and weigh it out, but it turns out it's a very hygroscopic material. That means that it absorbs water from the moisture in the air, so any reading you get on the scale is not going to be accurate. So instead, we want you to use potassium hydrogen phthalate, KHP, and this is the exact opposite, in a way, of the sodium hydroxide. It's a super stable crystalline solid, something that they call as an analytical standard, and it is used to compare other things to. So this KHP is going to stay consistent and safe, and it's not going to change its weight, sitting out in the air. So the first thing to do with our KHP is you want to first get a clean weighing paper and put it on your scale, and you want to tare the scale when the reading has kind of evened out. And your scales are probably going to be a little bit more accurate than the one I'm using here. You want to make sure to record every single sig fig. So as many digits as the scale says, you want to write that down. So right now I'm going to press the 0 button. Sometimes this is labeled as tare, and I want to zero out the scale. So right now this is zeroed out, and I'm ready to get some KHP loaded. So important thing to double check is on your online homework, they're going to tell you what's the range of KHP that you need to use, and that's going to be in the lab procedure. I believe it's from 0.5 to 0.6 grams, but that can change. So for sake of my demonstration today, I'm using about a ½ gram, and that's what we're going to use as our analyte. So in our titration, there's two key terms you should be aware of. One is the titrant and the analyte. The analyte is the thing that we're going to find out the concentration of using the titrant. So after weighing out our KHP, we're going to add it into our flask. And I want to make sure this completely dissolves. Sometimes you'll notice there's some KHP powder on the edges of the flask. You want to wash that down and make sure there's nothing on the walls of the flask. So now that we've added our KHP and dissolved it in some water, you might think that we're ready to go and begin the titration. Well, there's one more extremely important step, and that is to add in our phenolphthalein, which is the indicator. So phenolphthalein is going to actually tell us how close we are in the titration, and it'll allow us to determine the end point of the titration. So if you forget to add phenolphthalein, your solution is going to remain colorless, and basically it's going to be a waste of time. So without any further ado, let's get this started. I'm going to start at a relatively fast speed, and we notice that the color below is changing, but it's vanishing. It's becoming purple, it's vanishing. So now I'm going to stop this, give it a little bit of a swirl around, and we see that the color isn't really sticking. Let's add some more. So now you notice that purple color is kind of sticking around for a little bit longer. The longer the purple color sticks around, the closer you are to the end goal. So you want to be careful and slow down. So I don't know how clearly you all can see that, but this is the faintest pink color that is visible. This is exactly where you want to be for a titration. You could go a little bit farther, but this is so sensitive that even if I get a tiny bit of phenolphthalein, even if I get a tiny bit of that sodium hydroxide there and squirt it down, it's going to dramatically increase the color. So as you can see, that's what you're aiming for as like an ideal titration. I'm surprised that it was able to get that close, but for sake of demonstration, it's so sensitive that you could be a little bit off. There's one drop, and it dramatically increases the color. So I would say aim for something around here. You want to have a faint pink color. And what we're going to do is we're actually going to record our final volume. So right now I have 47.75. You can approximate in between two lines of the burette. So let's write 47.75. And we got to take the delta. So delta V of the volume would be 47.75. That's our final volume, minus 21. And in your notebook, you would write down 21.00 for sig figs. That means we have 26.75 mils of sodium hydroxide added. So we know there's 1,000 milliliters in 1 liter. So we want to divide this number by 1,000. And we get 0.02675 liters. And just to explain this formula again, we're finding out what's the concentration of this NaOH solution. We have the mass that we used of our KHP, which is half a gram, 0.50 grams. We have the molecular weight of KHP, which is 204.22, and we're multiplying that by 1 over the volume. So let me put this into the calculator and see if we get close to what I know this concentration is supposed to be. So we'll do 0.5 divided by 204.22, and we're going to multiply that by 1 over 0.02675. And that gives us 0.092 molar. Pardon my handwriting there, 0.092 molar, which is the obtained molarity of our NaOH solution. So I made this NaOH in April, and it's been sitting here. I made it to 0.0891 molar. And that tells us, even with this simple balance here, we're able to get pretty much the close accuracy of that NaOH solution's concentration. So it turns out that that's what you can use a titration for. We can't weigh NaOH accurately on the scale because its weight is going to keep increasing as water is absorbed in. So to get a reliable measurement of this concentration, we have to do a titration. The process I explained of basically determining what the NaOH is versus our KHP is called standardization. And this is what we do a titration for. Now that we know, after doing 2 or 3 trials of our NaOH concentration and getting an average, we can use this NaOH solution itself as a standard and figure out the concentration of other unknown things. I think we have unknown acetic acid solution. and other unknown acids that you can titrate with your NaOH, and you'll be able to figure out the concentration of those as well. So without any further ado, I wanted to give you a brief overview of the titration, go into some of the calculations. Again, my name is Zishan, and thank you for watching Temple Chemistry Demonstrated.